Welcome to this explainer. Today we're doing something really cool. We are going to decode the mathematical magic behind speech and language processing. And we're going to do it by solving a fascinating, kind of time-bending mystery. We'll see exactly how a very specific probabilistic model can help us uncover the invisible forces that shape the things we see every single day. Right off the bat, I want you to hook into this really wild idea. Can we predict past weather using only ice cream? It's a thought experiment designed by computer scientist Jason Eisner. Imagine it's the year 2799. You're a climatologist researching global warming, and you desperately need to know what the weather was like in Baltimore during the summer of 2020. But there's a catch. All meteorological records have been destroyed. The absolute only surviving evidence you have is a diary written by Jason Eisner himself, which meticulously records exactly how many ice creams he ate every single day that summer. So can we predict the past weather using only his dairy habits? I know, it sounds completely impossible, right? But this is exactly the kind of puzzle we're going to solve today.
Section 1. The basic Markov chain.
Okay, let's dive into this. Before we can solve our impossible mystery, we really need to understand the baseline mechanics of a regular Markov chain. It all starts with the Markov assumption, which is basically the golden rule in sequence probability. It states that when predicting the future in a sequence, the past doesn't matter, only the present state. Think of it like trying to predict tomorrow's weather, but you are literally only allowed to look at today's weather. You can't look at yesterday's or the day before's. A Markov chain makes this super strong assumption that the current state, the present, is absolutely all the information you need to figure out the probabilities of what happens next. But here's the critical complication. In a standard Markov chain, the events, like the weather, are completely visible to us. We can just observe them directly, tally them up, no problem. But in our 2799 mystery, the weather is totally hidden from us. All we can see are the resulting actions, which are the number of ice creams eaten, and that right there turns our mathematical model into a hidden Markov model, or HMM. The causal factors, the states, are completely invisible, and we only see the outputs, or observations, that they generate. So the crucial point here is that we basically have to work backward from what we can observe to uncover the reality that we can't. Section 2. The ice cream mystery. Let's transition over to the specific clues of our mystery to see how this works in practice. Again, imagine you're that climatologist in 2799 staring at Jason's diary. We need to outline the exact pieces of the puzzle we have to work with. Our goal is to estimate the summer 2020 Baltimore weather sequence. To keep the math clean for us, we'll assume there are only two hidden states. A day was either hot, represented by H, or cold, represented by C. Our observations, the things we can actually read in the diary, are entries of 1, 2, or 3 ice creams eaten daily. And that's it. That's our entire puzzle. And this brilliantly illustrates how we can map all these complex, abstract mathematical variables directly onto our concrete ice cream detective story. In a hidden Markov model, Q is our set of hidden states, hot or cold. A is our transition matrix, meaning what's the probability that a hot day changes into a cold day or, just stays hot. B represents our emission probabilities. Basically, if it really is a hot day, what is the probability Jason eats exactly 3 ice creams? And finally, pi is our initial distribution, which is just the probability of the very first day of the summer starting out hot or cold. So now that we have our variables, how do we actually solve the case? Well, in a really influential 1989 tutorial, researcher Lawrence Rabiner introduced the idea that hidden Markov models should be characterized by 3 fundamental problems. Think of these as 3 sequential hurdles our detective must overcome to completely master HMMs. First is likelihood, second is decoding, and third is learning. Let's tackle them one by one. Section 3. Finding the likelihood. We're going to start by tackling Rabiner's first problem, figuring out the likelihood. Basically, we need to know the probability of our sequence of clues actually happening in the real world. Let's say we open up the diary and see a 3-day sequence where Jason ate 3 ice creams, then 1, then 3. How likely is that exact sequence of observations? Now, if we knew the weather, we could calculate this super easily, just by multiplying the probabilities together. But we don't know the weather. Because we don't know the weather, we can't just trace one neat little path. We actually have to consider every single possible weather sequence that could have happened over those 3 days. Hot, hot, cold, 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 hot, and so on. And then sum up all their probabilities. For long sequences, this becomes an exponentially massive number of paths. It's just way too much math. So we use the forward algorithm.
This is a dynamic programming algorithm that essentially implicitly folds and sums every possible weather path into a single forward grid, or trellis. Instead of doing the math exponentially, it computes the observation probability step by step, super efficiently. It basically builds the probability up as it moves forward in time.
Section 4. Decoding the best path. But hey, just knowing the likelihood of the diary entries isn't quite enough to tell us what the weather actually was. We need to move from calculating general probabilities to actually guessing the hidden truth. And that brings us to our second hurdle, decoding. We know he ate 3 ice creams, then 1, then 3. But what was the absolute most likely hidden weather sequence for those specific ice creams? Was it hot, hot, cold? Or actually, maybe it was hot, cold, hot. How do we definitively decode the actual underlying reality from our observations? Now, what's really interesting here is that the solution, the Viterbi algorithm, looks almost identical to the forward algorithm we just used. But instead of taking the sum of all probabilities, the Viterbi algorithm takes the maximum probability path at each step. It asks what single path is most likely to get me to this current state. And crucially, as it moves forward, it leaves a trail of mathematical breadcrumbs, which we call back pointers. Once we reach the end of the diary sequence, we literally just follow those back pointers in reverse to trace the exact, most likely sequence of hot and cold days. Boom, we've decoded the weather. Section 5. Learning the parameters. But hold on a second. Both the forward and Viterbi algorithms, they assume we already have a cheat sheet. They assume we already know the probabilities of the weather changing and the probabilities of Jason's ice cream habits. But what if we don't? That brings us to the final and honestly hardest quest, Rabiner's third problem, learning the parameters. Just think about this challenge for a second. How do we learn the hidden transition and emission probabilities if absolutely all we have is a list of ice cream counts? We have 0 labeled weather data whatsoever. How can a machine learn these parameters entirely from scratch in a completely unsupervised way? The answer to that is the forward-backward algorithm, which is also known as the Baum-Welch algorithm. This is pretty much the ultimate detective tool for our hidden Markov model. It's an iterative technique called expectation maximization. Basically what happens is the algorithm makes an initial, essentially random guess about the probabilities, and then iteratively uses those very guesses to compute better and better estimates, literally teaching itself as it goes. Let's briefly break down how this brilliant little loop works. First up is the expectation step, or E step. Here the algorithm computes the expected state counts. It does this by combining the forward probabilities, which is looking from the start of the diary up to a specific day, with the backward probabilities, looking from the end of the diary back to that exact same day. Then we move over to the maximization step, or M step. It takes those newly expected counts to recompute and update the transition and emission probabilities so they're more accurate. It just repeats this E step and M step loop, continually refining its guesses for the weather and ice cream probabilities over and over again until the numbers literally stop changing. When they stop changing, we say they have converged, and our model has successfully learned the parameters. Okay, before we finish up, I just have to drop a fascinating historical Easter egg for you. Decoding hidden states is such a universally powerful concept that it wasn't just invented once. The Viterbi algorithm actually has a remarkable history of multiple independent discoveries across entirely different scientific fields. It was published for information theory by Viterbi in 1967, for speech processing in 1968, molecular biology in 1970, and for computer science in 1974. Brilliant minds in completely different domains realized, basically simultaneously, that this dynamic programming structure was the absolute ultimate way to uncover hidden truths in sequences. Which leads us right to our final thought. We've seen how hidden Markov models can logically reconstruct an entire lost summer of weather using nothing but a list of eaten ice creams, mapping observable actions to hidden realities. So, if an algorithm can mathematically decode the hidden weather of 2020 from a simple dairy habit, what hidden truths could it uncover in your own data? Thank you so much for exploring this explainer with me, and definitely keep looking for the hidden patterns around you.